right, how's everyone still feeling?
Totally awesome.
That's what I'd like to hear. So, let me show you a little video clip.
Hey, Sheldon, there's something I want to talk to you about before we go to the park.
I don't care if anybody gets it. I'm going as the Doppler effect.
No, it's not.
If I have to, I can demonstrate. So what time does the costume parade start?
The parade?
Yeah, so the judges can give out the prizes for best costume. You know, most frightening, most authentic, most accurate visualization of a scientific principle.
Oh, Sheldon, I'm sorry, but there aren't going to be any parades or judges or prizes.
This party is just going to suck.
Oh, but it's going to be fun, and you all look great. I mean, look at you, Thor, and Peter Pan. That's so cute.
Actually, Penny, he's wrong.
I'm Peter Pan!
I got a handful of pixie dust with your name on it.
No, you don't. I hate what Sheldon's supposed to be.
Oh, he's the Doppler effect.
Yes. It's the apparent change in the frequency of a wave caused by relative motion between the source of the wave and the observer. It's the apparent change in the frequency of a wave caused by relative motion between the source of the wave and the observer. It's the apparent change in the frequency of a wave caused by relative motion between the source of the wave and the observer.
Oh, sure, I see it now, the Doppler effect. All right, I got a shower. You guys, make yourselves comfortable.
Okay.
See? People get it.
Hi.
Hi.
Hello.
So what are you supposed to be?
Me? Go ahead.
Choo-choo train?
Close.
The brain damage choo-choo train? I still don't get it.
I'm the Doppler effect.
Okay, if that is some sort of learning disability, I think it's very insensitive.
Why don't you just tell people you're a zebra?
Well, why don't you just tell people you're one of the 7 dwarves?
Because I'm Frodo.
Yes, well, I'm the Doppler effect. It's the apparent change in the frequency of a wave caused by relative motion between the source of the wave and the observer.
All right, that's the whole clip. You guys, now, it doesn't really have to be a moving source. It really could be a moving observer. So, check this out here. This time the source is going to stay still. But if the observer starts approaching the source, notice how there's a shift in the observed frequency. Did you check that out? Look, watch. Like, pay attention to how many of those yellow waves cross by the person as he's approaching the source, and then how many of those yellow waves cross by the green person as he's moving away from the source. See, they were really high frequency. And now, look at this. What's up with the observed frequency now? Very low. What's that? No, he was moving across at the same speed the whole time. Yeah, but I don't think he did. It's the same speed. If you just focus on the two people. Did you catch that?
Yeah.
One more time? Alright, moving on. Okay, so finally, Dan takes out a little light bulb. And of course, the light bulb gives off light in all different directions. Now, normally with light, we only draw the rays. We draw the rays of light, leaving the light bulb. But now we know that we could also draw the wavefronts, which represent the crests of the waves. And they're going to be perpendicular to the rays, like this. And if that's a white light, and we had an observer over here, and we had another observer over here, guess what both of those observers would end up seeing? White light. Same thing being produced there in the middle. However, what if the source in the middle was moving? Now, I'm not going to draw the rays this time. I'm just going to draw the wavefronts. This time, let's say the source of the light was moving to the right. Well, if it was moving to the right, then the wavefronts over here would be closer together, and the wavefronts over here would be farther apart. So here the object is moving. And it's still giving off the same frequency, the same old white light. However, will the person over here observe the same frequency? Or is it going to be higher, or is it going to be lower over there? Higher. It's going to be a higher frequency, yes? Now with light, frequency doesn't correspond to pitch. That's a sound thing. With light, what does frequency correspond to in terms of what we see with the light?
Colors.
The color. And which color has the higher frequency? Violet. Now, I don't know why it's not called the violet shift, but blue is at that end of the spectrum as well. And a lot of times, the light over here is said to be seen more bluish. Even though it's a white light being produced, and Dan in the middle carrying the white light along with him, he would be like, yeah, this light looks white to me. But someone over here would end up seeing the light look more bluish. And that's called a blue shift. And an observer over here, how would they end up seeing that light? Sort of reddish in color. Maybe 2Ds? Reddish? Reddish. Or red shift. Yes?
Does the speed of the source matter at all?
Yes, Dan would have to be moving like 1/2 the speed of light. You know, he has to be moving really fast. So that's a very important point there.
That's why he did the
In order to see this with light, the source has to be moving pretty fast. You really couldn't do it just like running in the hallway. But, you know, this would have to be a pretty high velocity there. But here's the interesting thing. When astronomers on Earth study the stars with their telescopes. Look at this, yes? And they see stars over here, and stars over there, and stars over here, and a cluster of stars there, and a galaxy there. Guess which way the light, no matter which way they look, no matter where they are on the earth, guess which way the light is always shifted? You got 50-50 chance. Want to take a guess?
To the right.
No, is it shifted toward like a red shift or shifted like a blue shift? You think they see the light coming from the stars redder than usual or bluer than usual? Great try, but I'll give you a second try. Yeah, they observe the light with a red shift. Now remember, what does red shift mean? Red shift means, what is the source doing? Moving away. So if the light being observed from the stars is always shifted red, then what conclusion can we make about all the stars? They're moving away from us. Now, if all the stars and galaxies are moving away from us, what if you ran time backwards? What would all the stars be doing? Moving towards us and coming together, yes? And if you kept running time backwards, all the stars and material of the universe would come back to the same point. So this red shift Doppler effect is the number one evidence for what theory?
The Big Bang.
The Big Bang Theory. That's why I showed you that clip. Yes? The number one evidence that the universe originated at a point that, boom, blew up and has been expanding ever since is the Doppler effect. And the fact that no matter which way astronomers look, the light is always shifted red. Now, here's the thing. You might think, well, if everything seems to be moving away from us, are we in the center of the universe?
No.
Turns out, no matter where you are in the universe, guess what the light from all the other objects is doing? Moving away with the red shift. So remember at the second quarter when we talked about gravity and we talked about Einstein's space-time theory, where the whole universe was modeled as the sheet? Yes? The whole universe was modeled as the sheet. And remember we put a bowling ball on the sheet? And what did the bowling ball, the mass, do to the space of the universe? Made it curve and bend. Yes? Well, one story, one teaching that I always remember is you could think of the universe, that sheet, as being a balloon. Yes? Now imagine if I had a small little balloon and the membrane of the balloon represented our whole universe. And on that little balloon, I put dots. Dot, 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 dot. To represent all the stars and all the different, material objects in the universe. As I blow up the balloon, what would happen to the distance between all the dots? They would be going farther and farther apart. Is any one dot the center? No. No matter where you are, the whole universe is expanding. Einstein said it's not that the stars and the galaxies are moving farther away from us, but space itself is expanding. And that's why everything is moving farther and farther apart. But the number one evidence for the Big Bang is the fact that the light observed from any star is always shifted red. I'll get to your question in a second. What does that mean? The stars are moving away from us. Therefore, and then finally, if everything's moving away, if you ran time backwards, it would all go back to the same exact point. So this is the number one proof for the Big Bang theory. Question, Dana.
Is there not a hypothetical center of the universe?
Correct, there's not.
Well, I mean, if it all started at one point, then there has to be a center, technically, right?
No, but again, think of that balloon.
There's a middle of it.
Yeah, but the actual middle of the balloon, that's not even part of the universe. You know what I'm saying? It's the surface, and only on the surface is our universe.
If it all technically started at one point and it's all expanding from the one point outwards, then it's got to be that point.
But there's nothing there.
There's nothing there, but
Think of it as an
Well,
abstract.
you could, but it's not even a point in space. Because every point of space in our universe is in the membrane. Which is like really hard to comprehend. You know what I mean? Every single point in the universe, from as far as you can go this way, to as far as you can go that way, from as far as you can go this way, to as far as you can go that way, is all within the membrane of the balloon. Maybe another universe. So, very interesting stuff. We can say. If that balloon theory is correct, then if you did walk far enough in one direction, what should happen? You should come back from the other direction. Pretty weird, huh? Okay, so let's talk about how the Doppler effect is used to get speeders and all. Go up here. I looked high and low for an animation that would show this, and I can never find one, so I end up just making one myself. Let's see here. Alright, so it's basically just a PowerPoint, and I just scroll through it. Okay, so not the most beautiful thing in the world, but nonetheless, you can see. Alright, so you have this police officer hiding behind the tree with their radar gun, yes? And let's say the car out there is still, and they shine invisible light, radio waves, sometimes it's called radar. What's that acronym? Where's it? Radar. Radar is an acronym for radio detection and ranging. So, and let's see what happens when the car is still. The invisible light waves are sent out, and then they reflect off the car, and they come back, and that same little device can measure how they came back in. Yes? And notice, what's going to be the relationship between the frequency of the light that was released and the frequency of the light that was observed on the echo? It's going to be the same. Same frequency. So if the frequency is the same, the police officer knows the car is not moving. But now let's go to a moving car. Ready? What happened when the car was moving towards the police officer? Did the reflected waves keep the same frequency?
No.
They were greater, yes? And now watch what happens when the car moves away. So basically, an increase in the reflected rays indicates that the car was moving towards the radar gun, and a decrease in the reflected wave frequency indicates the car was moving away. And of course, we're going to have a formula momentarily that we could use to calculate exactly how fast that car is going. Let's go back, look through it one more time. All right, here we go. All right. Okay. So here's live Doppler radar right now. Notice not too many clouds over Long Island. Up in Binghamton, Syracuse. Looks like some clouds, maybe some showers, yes? Now, they keep showing over and over, so they go back like, you know, I don't know how much time it's actually looping back over. But when does it loop? Where does it say that? Oh yeah, thank you. 11:45 to what? 12:45. So it keeps showing the last hour. Now, how the heck do they know which way the clouds are going? Well, they have towers that send out invisible light, radio waves, and guess what this invisible light does when it hits any clouds? It reflects back. If it reflects back at the exact same frequency, then what does that little radar detector know? There's clouds, and what are the clouds doing? They're staying still. If it reflects back at a higher frequency, what is known about those clouds? They're moving towards. Now, usually you need more than one of those stations to triangulate exactly where the clouds are and which way they're moving. But this Doppler shift is exactly how they figure out these weather patterns. It's amazing. If you end up studying meteorology, you're sure to take a lot of physics, because a lot of physics going on with the technology being used to measure the weather and the physical structures like the Earth that you'd be studying. Okay, so let's get to the Doppler formula. This you're going to love. Now, as you'll see, I don't have this formula memorized, nor do you have to have this formula memorized. you probably will not have to use this formula on the AP exam. I just want you to be exposed to it so that you have a feeling for how this works. It's a little bit complicated, so let's check this out. Okay, so let's say we have the source of the waves, and over here we have an observer. Now let's say the source is moving with a velocity. V sub s is the velocity of the source. Now remember, that source is going to be producing waves. And the wave pattern might look something like this. But remember, the waves don't care that the source is moving. Once the wave is made, it just carries on as if nothing happened. It just keeps propagating or spreading out as it did before. So this very wave is actually spreading out. It's going this way, it's going this way, it's going this way, it's going this way. That wave is going to be spreading out. So the wave itself has its own velocity. And the velocity of the wave itself is simply called v. V is the velocity of the wave itself. If it is a sound wave, and we're studying the Doppler effect with sound waves, then v, without any subscripts, would be the speed of sound, 330 meters per second. So v sub s is how fast the source of the waves is moving. V is how fast the wave itself is moving. But here's the deal. We know that the observer could be moving as well. So we also have the velocity that the observer may have. And the observer could be moving closer to the source, or maybe the observer is moving away from the source. Now, by the way, if the velocity of the observer was in the same direction, same magnitude as the velocity of the source, then would there be a Doppler effect? No. No. It would be the same old frequency. So V sub O is equal to the velocity of the observer. Finally, we have F sub s, which is the frequency that the source is putting out. And then we have F sub O, which is the frequency that the observer is experiencing. Now it's a fun little derivation. It's actually not that complicated. A little bit of combination between the average velocity formula, v equals x over t, and the wave equation, velocity equals frequency times wavelength. But I'm about to give you the Doppler formula. We have all this down? And here it is. F sub O is equal to F sub S times, big fraction here, 1 plus or minus the velocity of the observer divided by the velocity of the wave itself, divided by 1 plus or minus the velocity of the source divided by the velocity of the wave itself. If it was actually a light wave, it's even a little bit more complicated because then you have to include the laws of special relativity. So this is like for a water wave or a sound wave, something not traveling near the speed of light. Now what about these plus or minuses? Okay, in the numerator, you use the plus when the observer moves towards the source. You use a minus in the numerator when the observer is moving away from the source. What about that plus and minus in the denominator? Plus is when the source moves away from the observer, minus when the source is moving towards the observer. So you would put in positive values for v sub O, the velocity of the observer, v, the velocity of the wave, and v sub s, the velocity of the source. But then you have to choose whether to use plus or minus, depending on whether the observer and the source is moving towards or away from the other. So I think for your homework, you're going to have to attempt to use this formula to get a feel for it. But on the actual AP exam, you only need to understand the concept. And of course, like police officers, when they use that radar gun, they're not doing these calculations. That's of course completely built in, and they just read the monitor. And it takes into account whether or not they're moving, because it's connected to their speedometer as well. And it takes all that into account to get how fast the car is going. So, in closing, What is the Doppler effect? It's when the observed frequency is different than the produced frequency due to the fact that either the source or the observer is moving. And for a moving observer. And let's look at one more computer animation. How much time do I have? Would you hit the lights again? Okay, so there's a jet, and there's a person on the ground observing the jet go by. And the first time the jet goes by, it's going 330 miles per hour. Wait, before you go, let's just watch what happens when it's 660 miles per hour. Let's go to 990 miles per hour. $13.20. Take care, guys. You're welcome. Homework 6.